All right, let's jump right into this explainer and crack open the highly technical and, honestly, sometimes pretty perilous hidden world of modern electric vehicle maintenance. For decades, automotive repair has basically been all about oil, gears, and combustion. But today, we're looking at a complete paradigm shift. We are literally dealing with rolling, high-voltage computers.
To really wrap your head around EV maintenance, you absolutely have to respect the power source. Modern EVs operate on 400 to 800 plus volts of direct current. That is a staggering amount of energy. It means the stakes of simply looking under the hood or pulling the wrong panel aren't just a burned finger or stripped bolt anymore. The stakes are immediately life or death. And that intense reality dictates every single thing a technician does.
So, here is our roadmap for today. We'll be covering 1. High voltage danger and safety. 2. Safe access and towing. 3. Unlocking diagnostics and inspection. 4. EV-specific maintenance quirks. And finally, number 5. Tracking fleet health. Let's get right to it.
Starting things off with Section 1, High Voltage Danger and Safety. This is absolutely the foundational knowledge separating traditional mechanics from certified EV techs.
Okay, if there's one golden rule, well, actually, scratch that. It's the orange rule. It's this. Manufacturers have universally agreed that if a cable, a harness, or a connector is bright orange, it represents the high-voltage DC bus threat. It demands absolute respect. You never split, splice, or modify any orange component without specific high-level certification. Period.
And to protect themselves when working near those orange lines, technicians rely on some incredibly specific PPE. Before they even think about touching a high-voltage system, they have to put on an air leak-tested pair of Class 0 rubber gloves. These bad boys are rated for 1500 volts of direct current, and they actually have to be physically tested for pinholes before every single use. Paired with that, as you can see, are VDE-certified tools featuring dual-layer, injection-molded orange insulation, because if you drop a standard metal wrench across high-voltage terminals, no joke, it will literally vaporize.
That covers standard operation. But what happens when things go wrong? Let's move to Section 2, Safe Access and Towing.
Think about this. What happens when the standard 12-volt battery dies and physically locks you out of this high-voltage fortress? Accessing a dead EV honestly feels like a sequence from a secret agent movie. The electronic doors and the hood latch are completely dead, so you can't just pop the hood. Instead, you've got to go to the front bumper, pry off this tiny plastic tow eye cover, and fish out a pair of hidden emergency red and black release wires. Then you hook a standard 12-volt jump pack straight to these tiny wires, which instantly triggers the electronic front latch so you can finally get in to jump the actual 12-volt battery. Wild, right?
Now, once you have power and get inside the cabin, technicians have to make the vehicles safe to work on. First responders might cut a specific loop under the hood during a crash, but techs, they use a much stealthier, non-destructive method. They lift the rear passenger seat to access a metal battery cover, affectionately called the penthouse. By disconnecting the low-voltage communication plug right there, they kill the control circuit to the internal high-voltage contactors. This safely isolates that massive battery pack.
But hold on. You can't just start turning wrenches the millisecond you pull that plug. Opening those contactors triggers the strict 10-minute rule. Technicians literally have to set a timer and wait a full 10 minutes to let the high-voltage inverter capacitors completely bleed off their residual electrical charge down to a safe 0 volts.
This brings us to another massive shift, towing. If an EV is dead on the side of the road, standard towing practices will absolutely destroy it. You can't just pop it in neutral and roll it onto a flatbed. It's called the no-roll rule. EVs use permanent magnet electric motors, right? So if you drag or roll the car with the drive wheel spinning, those motors instantly act as electrical generators. That back-fed current will push straight into the system and instantaneously fry the inverter. You either use a specific software transport mode, or you're putting wheel dollies under all 4 tires.
All right, now that the vehicle is powered up and safe to handle, let's dive into Section 3, Unlocking Diagnostics and Inspection.
So you don't plug a traditional scanner under the dash to figure out what's wrong with a modern EV. Why? Because the car is the scanner. To unlock the deep diagnostic testing for thermals, brakes, and the chassis, you go to the software menu on the center screen. You long press the vehicle model text for exactly 5 seconds. A hidden keypad drops down, and when you punch in the password, service, it's like entering a cheat code. The whole UI transforms, revealing every single sensor and system parameter in real time.
Once they're in service mode, technicians run through a very strict 5-step standardized workflow. Since EVs obviously don't have oil changes or timing belts, this routine, checking fluids and digital health, the interior, doing a road test, the under-vehicle lift, and finally wheels and brakes, is designed specifically to assess the unique mechanical and thermal stress points of an electric drivetrain.
What's really fascinating here is the incredibly narrow margin for error. Just look at the under-vehicle lift protocol. If a tech misses placing a designated rubber lift pad into the exact frame rail hole, the metal arms of the hoist will crush the plastic rocker panel inward and damage a multi-thousand-dollar high-voltage battery tray. Ouch. Also, while inspecting underneath, any deep structural dent on the battery skid plate isn't just cosmetic, it's an immediate, highly documented thermal and safety hazard.
Which brings us perfectly to Section 4, EV-specific maintenance quirks.
Let's see how these tight margins translate into everyday consumables, because they wear out totally differently than on a gas car. You might think a tire is just a tire, right? Nope. A heavy EV chassis combined with that crazy instantaneous electric torque completely changes the physics of wear and tear. Throw standard passenger tires on a high-performance EV, and they'll either completely disintegrate or wear bald on the inner edges in as little as 10,000 miles.
Because of that immense stress, replacement tires have to carry an extra load capacity rating. But here's the coolest part. As this illustrates, true EV tires contain a thick internal band of open-cell acoustic foam glued right inside the tread lining. Since an EV motor makes zero noise, standard tire slap and vibration would just loudly echo inside the silent cabin. That foam specifically absorbs those disruptive frequencies.
And get this, here is maybe the most ironic maintenance quirk of the whole bunch. Because EVs use regenerative braking, meaning the electric motors run in reverse to capture kinetic energy and slow the car down, that system handles up to 90% of your stopping power. The result? The physical brake pads barely ever touch the rotors. So if you live in a snowy, salted region, you actually have to pay a tech to grease the brakes every year just to stop them from rusting solid, purely from a lack of use.
Even something as completely mundane as changing the windshield wipers is highly technical. You can't just grab the wiper arms and pull them up. You have to go into the screen and activate wiper service mode to park them vertically on the glass. If you just force them up by hand, the arm will strike the razor-sharp edge of the aluminum hood and gouge the paint. And worse, if that bare metal arm snaps down without a blade attached, it will instantly shatter your windshield.
All right, let's wrap things up by zooming out to Section 5, Tracking Fleet Health. We've talked a lot about physical wrenches and safety gloves, but today, the ultimate tool is data. Repairs are logged in vast databases against the battery's overall state of health and the millivolt delta, which is the tiny voltage difference between individual battery cells. By tracking these super-specific metrics in collaborative tools like Google Sheets, fleet managers can spot cell degradation trends across thousands of vehicles. They can literally pinpoint a failing battery module weeks before the driver ever sees a warning light on their dashboard.
Which leaves us with this final thought to consider. As our cars evolve into infinitely complex, rolling high-voltage computers, the true tool of the master technician really isn't just a wrench or a lift or even insulated gloves anymore. It's the data. Are we moving into an era where we fix our cars before they even know they're broken? It certainly looks like it. Thanks for hanging out with me for this explainer, and keep questioning the technology that drives us forward.